What is up, you guys? Welcome to the 22nd lecture of this course entitled Convex Optimization. In this one, we'll be talking about strong alternatives, which strengthens weak alternatives, right? So we're going to see what are the conditions that allows us to state strong alternatives of two systems. We're going to be talking about the case of strict inequalities and non-strict inequalities, and we're going to be giving two applications that are linear inequalities and intersection of ellipsoids. So without further ado, let's get started. So in this lecture, we're going to extend or strengthen weak alternatives, a concept that we talked about in the previous lectures. So in the previous one, we introduced the concept of weak alternatives, and to sum everything up, we said that at most the two set of inequalities T and S are feasible. So if one is feasible, the other isn't feasible. But we cannot say anything in this case about infeasibility. So if you figured out that T is infeasible, this is inconclusive. And likewise for S. You can only assert a statement or feasibility about one set if you know that the other is feasible. Now, in strong alternatives, you can say this if becomes an if and only if, which means that you can say stuff when the set, either set S or T, are infeasible or not. So weak alternatives happen when, or you can only say that you've got weak alternatives only when Fi's are not necessarily convex and Hi's are not necessarily affine. So when you impose the constraint, when you come and tell me, okay, I've got the set of inequalities S, where now my Fi's, let's say now, my Fi's, I know that they are convex, right? And I also know that my hi of x are affine. That is, my hi of x looks something like ax minus b, right? If I know this piece of information, as well as this, and one more thing, that is that there exists an x that falls in the relative interior of the domain of the problem D, okay? Such that ax is b, then we can strengthen those weak alternatives. That is to say, my T, which now looks like this, so my T initially was, or let's start with S because S is more straightforward. So I've got my S that looks like Fi of x less than or equal to 0, where I runs from 1 till m. And what else do we have? My hi of x's are affine and thus take the form ax minus b equals 0 or ax equal b, right? So and ax equal b. So this is my set S. And my T right now would look like this. So my T was lambda positive, right? There it is, lambda positive. And G lambda nu strictly positive, right? Let's say I want to color them to stay consistent. So my S is blue and my T is red. So now we're dealing with those two sets. The only thing that differs is the fact that my hi of x's are now ax equal b because they're affine, and my fi's are convex. Okay. Now what I can say is the following. So if S is feasible, then this is two-way. Then, actually we don't need an if here because this is an if and only if. So I'm going to erase this, right? So if S is feasible, or S is feasible if and only if T is infeasible, right? And likewise, T is feasible. This is just the negation of the first statement. So negate both. You'll get T is feasible if and only if S is infeasible. So this is what we call strong alternatives. It's when exactly one of the two systems is feasible. Weak alternatives tells you that at most one is feasible. However, in strong duality, it tells you that exactly one is feasible. Okay? So this is what we mean by strong alternatives only for the case of non-strict inequalities. So over here you see that this is not strict. Now in case this is strict, you can do the math as we did in the previous lecture. So for the case of strict inequalities, when we say strict over here, this applies for the FIs. So in case my FIs are strictly less than 0, that is, my S would look something like this. So my Fi of X is strictly negative when I'm dealing with this kind of set, and AX is B when we're talking about this set, and my set T would then take the following form. So lambda is greater than or equal to 0, no problem. We have to, so keep this in mind. When S is non-strict, then T is strict. Now likewise, when S is strict, then T doesn't have to be strict. Okay, so now let's see where we could use this. So in linear inequalities, my set S doesn't contain any equality constraints, okay? So that being said, my S looks like this. AX less than or equal to B, okay? So in this particular case, if we want to derive T, which looks like this, so again, be careful here. This is non-strict inequality. So you'd want to apply this over here. So my T would look like this. Lambda is greater than or equal to 0. And my G, lambda, nu is strictly positive, right? I know my S, but I don't know my T. I need my dual function, right? So over here, since I don't have any equality constraints, then nu is useless. So my G should only contain or only contains, lambda, right? Because lambda is penalizing the only constraint AX less than B. Okay, let's write down lambda, G of lambda, that is the infimum over X in the domain of the problem of the Lagrangian function, Lx lambda. That is the infimum over X in D of my f0 of X is 0, because we're minimizing 0, And we have only one inequality constraint, that is ax less than b. So it will be lambda transpose times this thing less than 0. So ax minus b less than 0 as such. Now, if you want to expand this to see it more clearly, we did this multiple times throughout this course. We did the infimum of lambda transpose ax minus lambda transpose b multiple times. And this guy is actually, if this term is 0, then you're taking the infimum over a constant. So this term is 0 from lambda transpose a equal to 0. So if lambda transpose a is 0, then we're left with minus lambda transpose b. Else, you can always pull this term down to minus infinity, and hence your infimum could be minus infinity otherwise. Okay? So this is my g of lambda. And now we don't care about the minus infinity case because we don't care. So we're left with this guy. So my t now looks like this. I could write it as lambda positive. We need this condition so that we could say that my g of lambda takes this finite form. So lambda transpose A is 0. And this guy should be strictly positive. So minus lambda transpose B is strictly positive. Now let's say you have the same exact problem, but this time with a strict linear inequality. So let's say now your S is defined as AX strictly less than B. Well, doing the math, you could arrive at the same exact solution over here, but with non-strict inequality over here, and lambda is non-zero. So lambda greater than or equal to 0, but it cannot be 0. Lambda transpose A is 0. And lambda transpose B is allowed to be 0. So lambda transpose B is less than or equal to 0. So why do we care about S and T over here? It means that one of the two is feasible. Now this is not new. We saw this in different contexts. And in particular when we tackled the theorem of separating hyperplanes. So in separating hyperplanes, applied on system of strict linear inequalities. So for the case of AX strictly less than B, you could actually see this inequality as an intersection of two sets. So let's define two sets, call them C and D. So C is defined as the set of B minus AX. Actually, this guy could also be written as B minus AX strictly positive. So the first set is C is B minus AX, where X is an Rn. And the second set, D, is all vectors Y such that they are entry-wise positive. Okay? The set of solutions of AX less than B, or equivalently B minus AX strictly greater than 0, is characterized by the intersection of both sets C and D, right? So your solution is found in C intersect D, okay? Now, let's take a closer look at both sets. Both sets are convex, right? Why? Because C is affine and D is not only convex, but it is also open. So we know from the theorem of separating hyperplanes, so using the theorem of separating hyperplanes, that if both sets do not intersect, there is a hyperplane separating them at least. And this makes sense. Let's say this is C. Oh, sorry, C has to be convex. So let's say this is C and this is D. Okay, imagine that both sets are convex. So if this is my D, this is my C. There is a hyperplane separating them with a certain gradient, which in this case will be lambda, and a certain intercept, which in this case we'll call, I don't know, alpha. Okay? So what we're trying to see here is that exactly one of the two sets is feasible, S and T. We wrote S as an intersection of, C and D. And we're in the case where, C and D do not intersect. So if they do not intersect, means that S is infeasible. So if this is phi, if this is empty, means that S is infeasible, which means that there is a hyperplane separating C from D. And this is actually written down as follows. So there exists a lambda in, say, Rm, and this is the gradient, and an alpha, the intercept, in R, such that lambda transpose Y is less than alpha on C, and the same term is greater than alpha on D. Okay, so greater than alpha means we're down, so we're in D, and less than alpha means we're up, means we're in C. So what does this tell us? Well, if we're in C, means my Y could be expressed as B minus AX. So this means that lambda transpose B minus AX is less than alpha, right? For all X in Rn. Now, expanding this term, lambda transpose B minus lambda transpose AX less than alpha. But a linear function is bounded below on Rm only when it is 0. So this guy is bounded below only when it is 0. And hence, lambda transpose A has to be 0. Okay? This means that lambda transpose B is less than alpha. Now, applying this on D, what do we get? On D, we have that lambda transpose Y is greater than or equal to alpha for all Y that is strictly positive, as set D tells us, right? And so be careful over here. So this applies for all positive Y's, okay? All positive Y's. So if I'm sure that this term is positive for all positive Y's, if this is positive all the time for all positive Y's, that is for if my lambda is all positive and non-zero, then there is no positive alpha that could maintain all those guys to be positive. We could always find the lambda transpose Y that is less than something positive. Alpha should be picked in the negative sense. Okay? At the most, it's 0. Now, combining what we got here and here, what we get is this. So if my lambda transpose B is less than alpha, which is itself less than 0 over here, and lambda positive, where lambda is non-zero, right? This is over here. And we had one more condition right here. That is lambda transpose A is 0. This is my set T, right? This is set T. So we don't care about alpha, right? All we care about is lambda transpose B is less than 0. So this finally means that T has to be satisfied. T has to be feasible, right? This all followed from the theorem of separating hyperplanes, which in turn followed from the fact that C and D do not intersect, which in turn means that S is infeasible. So if S is infeasible, then T is feasible. And that's another way of seeing the theorem of alternatives on strict linear inequalities. Okay? Now another application over here is the intersection of ellipsoids. Okay? Let's say we have a set, call it EI, that is all x's that fall within fi of x less than or equal to 0, where my fi of x is equal to x transpose ai x plus 2 bi transpose x plus ci, and my ai's are positive, definite, and symmetric. And the main question over here is, when is E1 intersection E2 intersection down to EM, the set, when is this set non-empty? When does it have a non-empty interior? In other words, when is the intersection feasible? So for that, let's pick this as my set S. So my S is E1 intersection E2 down to EM. And so, since we have non-strict inequality, then my T would look like this. So going back up here, would be lambda positive and G lambda strictly positive, right? So for that, let's write the dual function. That is the infimum of x in the domain of the problem of the Lagrangian function Lx lambda as such. So what is my Lagrangian function? We don't have an f0 of x, right? All we have is non-strict inequality constraints. So it's the sum I going from 1 till m of lambda I fi of x. Let's replace fi of x. So my fi is x transpose ai x. It's what we have over here. Plus 2bi transpose x plus ci, right? Now we can expand this sum as such. So I running from 1 till m lambda I x transpose ai x plus sum 2 lambda I bi transpose x plus a sum of lambda I ci. Now we can write this in a different way that is nicer as x transpose sum over lambda I ai x. So this is a central matrix plus sum or plus 2 sum lambda I bi transpose x plus a sum of lambda I ci, right? Now we can denote this guy by a matrix A of lambda, this guy by a vector B seen through lambda, and this guy as a scalar C of lambda, so that we have the following form. X transpose A lambda of x plus 2 B lambda transpose x plus C of lambda. Okay, so the question here is, what is the infimum of this guy? Well, using basic calculus, you could set the gradient with respect to x of the Lagrangian function to 0. That is, the gradient of the first term is 2a lambda x, and the gradient of the second term is 2b lambda. Set it to 0, you will get a lambda x is minus b lambda. Now to get x, we multiply by the inverse of a lambda. We're allowed to do so because it's square. And this is your x star. Now to get the infimum, we have to plug in x star in the Lagrangian function. So what we get is x star transpose a lambda x star plus 2b lambda transpose x star plus c lambda. Now plugging in the expression over here, we get b lambda transpose a inverse lambda multiplied by a lambda multiplied by x star, that is in turn a inverse lambda b lambda. Notice that I didn't mention the minus because we've got two minuses over here, so they cancel out. Also, we've got an a lambda inverse multiplied by a lambda, which gives us the identity matrix, right? We continue the math over here. 2b transpose lambda, x star is minus, so this guy over here becomes a minus. And we've got an a inverse lambda multiplied by b lambda plus c of lambda. So what we get is b transpose lambda, a inverse lambda, b of lambda minus 2b transpose lambda, a inverse lambda, b lambda plus c of lambda. So we've got 1 times a term minus 2 times the same term. This gives us 1 minus 2, that's a minus 1, multiplied by b transpose lambda, a inverse lambda, b of lambda, plus c of lambda. Now this is my g of lambda in the case where a is invertible, that is equivalent to A lambda being positive definite, and that B falls in the range of A of lambda. And why do we need that? It's because to have that this system over here admits a solution. So this is true only when B falls in the range of A of lambda. Otherwise, the infimum is just minus infinity. You could just pick x as small as possible. Okay, so this is your g of lambda. Now you could write down t, the set t that is lambda positive, and g of lambda positive. So minus b transpose lambda, A inverse lambda, b of lambda plus c of lambda is positive. And of course, you're going to require that your A of lambda is positive definite, and you need that B falls in the range of A of lambda. Okay, so this is your set T corresponding to set S, that is initially E1 intersection E2 down till EM, right? But there's a tiny mistake that we did. And what is that? It's because when we take the intersection of the sets over here, then this less than or equal becomes a strict inequality. So over here, we're dealing with strict inequality. So this guy translates to the case of the strict inequality, which is this guy over here. So lambda shouldn't be 0. That is what we should add as well. So over here, lambda is not 0. So to fully answer the question, and we're allowed to do all this because we're allowed to write down the t, because all my e's are convex, right? This set of inequalities, fi's are convex, because ai's, this is quadratic and hence convex, because ai's are positive definite, symmetric positive definite. So to fully answer the question, when is the intersection of all my e's non-empty, it suffices to say that t should be infeasible. So when you cannot find a lambda satisfying t, all this is the equivalent to say that S has an unempty interior. Now on the other hand, S is infeasible or has an empty interior when T is feasible. And that's it for this lecture. So in this one, we talked about strong alternatives. That is, we took the weak alternatives from the previous lecture and we added a couple of conditions such as Fi is convex, Hi is affine, so Hi is Ax equal minus B, and X, there exists an X in the relative interior of the domain of the problem such that Ax is B. Then we could replace weak by strong alternatives. That is, exactly one of the two sets S and T is feasible. When you find one is feasible, the other is infeasible. This is indeed stronger than weak alternatives because my if condition becomes an if and only if. So not only could we say stuff about if we pick one set to be feasible, then the other is infeasible, but we can also insert that if we find a set that is infeasible among the two, then the other one, we could be sure that the other one is feasible. That said, exactly one of the two sets is feasible and the other is infeasible. So we also talked about the case of strict inequalities. Notice that here we have non-strict inequality. So when this guy becomes strict, then automatically G becomes non-strict. Okay? We gave examples on linear inequalities, so inequalities of first order, Ax less than B. We saw that its corresponding T set would take the form, as you can see over here. Lambda transpose B is less than 0, lambda transpose A is 0, and lambda is a non-zero positive vector. This is another way of stating the theorem of separating hyperplanes. So we saw that actually we can derive strong alternatives of set and T using the theorem of separating hyperplanes. That is, if we define AX less than B in another way as an intersection of two convex sets, C and D. So C is the set of, all vectors that take the form B minus AX, where X moves in Rn, and D is all positive vectors in Rn. If you define such an intersection, you're actually solving this system of strict linear inequalities. Then we can define T using the theorem of supporting hyperplanes. And last but not least, we give an application on intersection of ellipsoids. So system of linear inequalities of second order. We saw its corresponding T set to answer the question that when is this set E1 intersection E2 down to intersection EM, when is it non-empty? When does it have a non-empty interior? It turns out when T is infeasible. So when T, that we derived over here using the dual function G of lambda, right here, when this guy is positive, along with those conditions, A lambda being positive definite, and B falling in the range of A of lambda, given that lambda is a non-zero positive vector, then if this set is infeasible, then S is feasible, and hence the intersection of all the ellipsoids forms a non-empty interior. Thanks for watching. I hope you found this lecture beneficial. If you did, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.